Hello, my name is Hussein Darir. I'm a PhD student at the University of Illinois at Urbana-Champaign under the supervision of Professor Geir Dullerud and Professor Nikita Borisov. Today I'm going to present our paper called MLEFlow, Learning from History to Improve Load Balancing in Tor. Privacy is a major concern nowadays. It has been consistently on the headlines of news in recent years. Many technologies are emerging to ensure data and people privacy. An example of a successfully implemented technology that seek to create a certain level of privacy to users are anonymous communication networks. Users are increasingly turning to anonymous communication networks to protect themselves from surveillance and online tracking. Anonymity networks provide users a way to communicate without revealing their identity and without revealing their relationship to third parties. Tor is the most popular anonymity network. Tor is a free software, open source, and run by volunteers. It has millions of daily active users. To create a connection, a user chooses a path of 3 different relays to construct a circuit that forwards traffic in both directions. Only the user knows the entire path. The relays know only their predecessor and successor, obscuring the relationship between users and destinations. The traffic is also encrypted and decrypted at each node to hide the correspondence between incoming and outgoing traffic from a network observer. Despite the advantages offered from a privacy point of view, Tor can be slow. It can be due to imperfect path allocations that we dealt with in a previous paper, or to inaccurate relays capacity estimation that we deal with in this paper. So as an outline to this presentation, I'm going first to present the current path allocation algorithm used in the Tor network to show the importance of having accurate capacity estimations. Then I will present our maximum likelihood capacity estimation algorithm that we call MLEFlow. And then I will present the results of shadow simulations that compares the performance of MLEFlow when compared to other deployed algorithms for capacity estimation. So first, starting with the current path allocation algorithm used in the Tor network. Currently, the Tor network uses a randomized assignment of flow circuits to relays, where each user chooses the relays for their circuits randomly, weighted by their estimated capacity. An incoming user will use the random algorithm to choose the 3 relays forming their path. The random algorithm receives the relay capacity estimates from the relay capacity estimation algorithm and creates a probability distribution over the relays. This distribution is then sampled to choose 3 distinct relays that the user will use to serve the internet. The intuition behind the random algorithm is that if the estimated capacities are equal to the true capacity of the relay, the expected number of paths using each relay will be proportional to its bandwidth. Relay capacities are currently estimated using TorFlow. TorFlow relies on 2 types of measurements, the self-reported bandwidth and the measured bandwidth. This version of capacity estimation has been in use in Tor since 2012. So starting with the self-reported bandwidth, each relay estimates its own network capacity by computing the maximum sustained download and upload bandwidth over a 5-second period over the last 5 days, and reports this value to directory authorities. The self-reported value is then adjusted based on the result of a probe, which we will call the measured bandwidth. Directory authorities create probe circuits through each relay and download a file measuring the realized bandwidth of this probe. TorFlow then uses both those measurements to estimate the capacity of a relay J. Those estimates get recomputed once an hour, and we will call that an epoch. This method, however, has a number of disadvantages. A relay that is not sufficiently loaded may underestimate its self-reported bandwidth. This leads to a well-documented ramp-up period of new relays, where their low self-reported bandwidth leads to a small estimated capacity and hence low load, which in turn leads to low self-reported bandwidth. But even established relays see their self-reported bandwidth change over time, as can be depicted in this plot of the self-reported bandwidth of 10 randomly selected relays in the Tor network over the months of May 2020. An additional problem is that the use of self-reported bandwidth makes it possible for a relay to influence its estimated capacity. Using the self-reported bandwidth for load balancing creates the opportunity for a low-resource attack on the Tor network. In particular, a relay can publish a high self-reported bandwidth for itself, which will cause more clients to choose it and creates more chances for it to break users' anonymity. A previous configuration of TorFlow did not use self-reported bandwidth. Instead, it adjusted the previous weight based on the current observation and the last estimated capacity. The intuition is similar. If the current weight of the relay is too high, it will have a below average performance and hence a below average measurement, and its weight will be adjusted down, and vice versa. We will note that Tor switched away from TorFlow P because when deployed, the feedback mechanism allowed the weights to significantly deviate from network capacities. A recent effort to upgrade and re-engineer TorFlow has resulted in the development of SBWS. SBWS still uses the self-reported bandwidth and measured bandwidth, however it takes the minimum between the self-reported bandwidth and the estimated capacity. This makes the SBWS implementation a hybrid between TorFlow and TorFlow P. It's still susceptible to underweighting relays with low self-reported bandwidth, but it's more resilient to self-reported bandwidth that is too high. Now I'm going to present our maximum likelihood capacity estimation algorithm that we called MLEFlow. For any relay J in the set of all relays in the network that we call N, the MLE estimate of its actual capacity that we call C star of J will be a capacity kappa in the set of real positive number that maximizes the probability of observing the full history of measurements, MT of J, given the published weights, WT of J, over the first T+1 epochs. This can be formulated as the argmax of this probability. As assumptions to our model, we consider a model where each user path goes through a single relay instead of 3 relays. We consider also a synchronized model where time is divided into epochs and user connections all terminate at the end of each epoch. Users' arrival are Poisson distributed with rate lambda s, so given the weight, Wt of j, the number of paths using the jth relay during the tth epoch is a random variable, xt of j, that is Poisson distributed with parameters lambda s Wt of j. Clients use all the bandwidth allocated to them. We also assume that we have a bounded capacity set with known bounds. Using the model assumptions that we just presented, since we are only considering single relay paths, the capacity of a relay will be divided equally among all the paths passing through it, and hence we can relate the measured observation MT of j to the actual capacity of the relay C star of j by dividing C star of j by the number of paths passing through the relay xt of j plus 1, where this one refers to the prober created by the directory authorities. Hence, using this relationship, we can write the capacity estimate as the argmax of the product of Poisson probabilities. And hence, we can do this maximization over the quantized capacity interval that we already defined. Using Stirling approximation, Lambert-W function, and Taylor series expansion, we can find an approximation to the closed form solution of this maximization, which we call MLEFlow CF. If we consider the equation that we just presented, and we suppose that the estimation only used the most recent measurement, and therefore I is equal to t, we can find this equation for the capacity estimation at t plus 1. If we normalize, we'll find the weight at t plus 1, and if we compare this weight to the weight obtained after normalizing the estimated capacities of TorFlow P, we can see that TorFlow P is actually equivalent to estimating the capacities using MLE, considering only the last measurement and then normalizing to get the weight vector. Hence, while TorFlow will only use the last measurement to estimate the capacity of a relay, MLEFlow will take into account the full history of measurements. Hence, we can compare both those algorithms, and we find that for both algorithms, for any relay J, the expected value of the capacity estimates will go to the actual capacity as the rate of arrival of users goes to infinity. We also find that the variances of MLEFlow closed form estimates are always less than the variances of the estimates found using TorFlow P. And as t goes to infinity, the variance of the MLEFlow closed form estimates will go to 0. I'm going now to present our shadow simulator result. We considered a 3% Tor network that contains 196 Tor relays. We simulated our network for 22 epochs with a rate of arrival of 2000. In this graph, we compare the error between the actual capacity and the estimated capacities when using MLEFlow, TORFlow, and SPWS algorithms. As we can see, for the three different classes of relays, guards, middles, and exits, we can see that the error when using MLEFlow is much lower than when using TORFlow P and SPWS, especially for exit relays, for example, where the error average was around 5% when using MLEFlow, while it was around 30% when using TORFlow P and above 80% when using SPWS. An important question is, how does this affect the performance of Tor users? In fact, using shadow simulations, we found that around 75% of all clients using MLEFlow Q estimates achieved a higher bandwidth compared to clients using TORFlow estimates. So as takeaways from this presentation, MLEFlow ensures a fairer and more accurate bandwidth allocation in the Tor network. MLEFlow uses the full history of measurements. It leads to more accurate relays capacity estimates and fairer bandwidth allocation between users. We showed that our theoretical results were validated using both low fidelity and high fidelity simulations. Thank you.